but if you can't do it, well, if half of the nodes can't have incoming connections, if just half of the nodes can have incoming connections, then I can connect them in a random network, and half of the nodes will be parasitic, so to speak, half will do other part, and that works. But if you say it will reach like 90% of the nodes can't take incoming connections, then there's no real way around that. But as long as like half or 1/3 or half of the nodes can receive incoming connections, we can handle that. And I'll talk about that and show why some of those are better from that viewpoint. Because that's why some are too bad, because I'll take that into account. So I'll talk about that.
Yeah, what I'm thinking of is mobile phones.
Yeah. So yeah, it's probably an increasing problem again.
Yeah, because a lot of people are going to be using these and not computers.
Well, connections will be more transient.
Yeah.
But I can handle transient. But I'll show you that. But there's a limit, of course. There's a limit. If too many of the nodes can't take incoming connections, then we can't do anything about it. Then we have to simply start locking those nodes out and just let well-behaving nodes take part. We have to complain and they have to fix that. We shouldn't, but we'll get into that more later. By the way, now this is just 1 hour talk to get an overview. Then we'll get deep into every subject. I forgot to tell them. So the next 2 days, this day and tomorrow, we'll pick apart every part of this. Hopefully we'll have time to pick apart all the parts, but we'll see how far we get. Because I haven't timed myself for planning so well, so we'll do what we can. Yeah. So, network structure. And this is network structure is kind of the thing that most people fail at. And especially those university systems like that. Because with the right network structure, you can handle almost anything. With the wrong one, you're stuck doing just some things. No one uses that one, but this one is an easy example to understand the problem with some of the network structures. The two-dimensional grid. It's very easy to understand. Each node has 4 connections to 4 neighbors, and you just connect them out to a grid like that. But so we humans, we can grasp these structures very easily, but they're tricky to code and maintain because look up here. One node just left. There's a hole. We have to fill in that hole. For instance, we can take one of those in the corner and move it there, so we can get a consistent grid. But that means lots of messaging traffic. The nodes have to be smart, understand this, and fix this. So it becomes many message types, so it's very chatty and lots of code. Yeah. But also, this particular structure is inefficient because most of the things we do are actually kind of broadcasting. And if you broadcast a message from the corner, it takes a long time until it reaches the other side of the network. So a two-dimensional grid is really stupid. Hypercube, it was actually the big hype back then, in 2001 or 2002. Hypercube is also a grid. Everyone knows what a hypercube is, I think. You know what a normal cubic graph dimensions. So if you just make many dimensions to room all, to have space, address space enough for all the nodes in the network. So this one is also fairly easy to understand. At least computer will usually understand it almost immediately. But it has the same problems as the two-dimensional, well-ordered grid. It's tricky to maintain in code because if some node disappears, you have to fill in that hole. And if the network shrinks, you have to remove one of the dimensions and put it together. So it's very chatty, many message types, very chatty. So it actually costs fairly much bandwidth just to maintain it when you're idling. And then also, but this one is fairly efficient at least because broadcasting of this one is, there's no node is far away. So if some node is broadcasting the message to the whole network very quickly. And you can also route on top of this. So you can use this as a routing overlay. If you don't know what a routing overlay is, don't worry, we'll talk about those later. So I can't explain that shortly enough. But, so this is routable. So it's fairly good, but it's also a slightly inefficient routing overlay. So we have better stuff now. So I don't recommend this either. This is what I recommend. This is kind of my favorite. A random network or a small world network. A random network means that a node connects to 5 other nodes, randomly chosen from the whole population. So if there are 1 million nodes, you just pick 5 of them and connect to them. And if you do that, you get a random network. There's some tricks to that because if you do it in the wrong way, you get some weird things happening, and I'll give you how to do that properly, avoid the traps. But that's a random network. In this case, it's 3 links to every node. But a small world network, well, many people have been talking about small world network. And that's actually a random network with some cluster. That most of your links are going to friends, close friends in some way, geographically or some other way. And then you have some distant links. And the distant links means that the whole network sticks together. And when you put things on top of that, the algorithms have to put on top. Actually, it's the same thing. So random network to small world network doesn't matter for me, because you can broadcast on it and you can send things on it. These network structures are somewhat hard for humans to understand. Our brains don't want to grasp them. But they're really easy to code and maintain. My algorithm to building such a network and connect it and maintain it is 1 page of code. That's all. It's a small loop that does the work. It's really simple algorithm, really simple code. And also, it's just 1 message line. You don't need it's not sharded. You just send 1 message type once a minute. That's about it. So you can maintain this very cheaply. And these ones are extremely efficient. Broadcasting, the distances across this network is actually shorter than on a hypercube. So this is more efficient than the hypercube. And this is actually the second most efficient network structure there is, as far as we know. There is 2 other networks that are more efficient in 2 other ways. One's that only costs 1 connection, and another one that has shorter jump distance compared to a number of connections. But the one that has shorter jump distance is well ordered and easy to crash. It's hard to maintain. So this is the second most efficient, and this is the one I will be using for all our examples later on. Let's see what I want to go to say about these ones. Yeah. Back when I started my research, most people were doing something like that, or some other well-ordered structure. Because they're easy to understand, and most people thought that was the proper path of solutions. But since I happened to stumble on these ones and started to realize I could do stuff there, I thought it was harder to do, so it was more fun. And since almost no one else was doing it, back then I think it was 2 or 3 other teams that were doing it. So I had almost no competition, so I thought if I go down there, I might be the first one solving it. And I did solve it. I think now I'm pretty almost can guarantee that this is the better path. It seems so, at least to me. So all the algorithms will be of this kind. But I can't prove it. It might be that someone will come up with a good well-ordered structure that is better, but so far no one has. So I'm still voting on this path. So. Well, there's, as I said, many different problems that we have to solve. One of the main problems that most networks have is net splits. That is, the nodes tend to group in islands, and the islands lose their connection, and when they have separate islands, they stop communicating. For instance, the Kazan network back then, when the start server, well, they had some servers to keep it together because they had these problems. They added some servers that helped keeping the network together. And when they went offline, it took some hours, and the network just fell apart in islands. And after 1 or 4 days, didn't find anything in searching because the islands were too small. They actually kept falling apart. So in the end, we were on an island with 10 nodes or 100 nodes or something like that. So we have to prevent net splits. We have to make the network hanging together. And on a random network, some are unordered networks, there's 3 ways to do that. The first one, that was used by the way, how many here have heard about the Nutella network? Okay, yeah. The Nutella network, for you that don't know, it's basically a random network, and we broadcasted searches of that, so to find files and download those files. And that was the first, as far as I know, serverless file sharing network. It came in spring 2000, I think. And that one, to find, when you want to do new connections, they have to be randomly from the whole set. Otherwise, if it just shows too close, you get this. For instance, if this node loses a connection, what new connections shouldn't shows connection nearby, should preferably get a connection to the other side. So one way to do that is to use a node address announcement, or a node ping, or whatever you call it. It is the node puts together a small message with its own IP number and port number and stuff like that, and it sends it randomly to one of its neighbors, and the neighbor sends it on, and it 10 jumps away from the node. And that node that gets it 10 jumps away takes it and stores it, and then it learns about a node that is randomly 10 jumps away in some random direction. So in this case, if you have a network with average 5 connections, then you have to send for 10 jumps. If you have more connections, you can limit the number of jumps. So the more connections you have, the less number of jumps you have to do with these messages to keep it stable. And for instance, if it's a random network, the minimum number of links you can have is 3.6 links. That is, most nodes have 3 and some have, most nodes have 4 connections and some have 3 connections. If you go below that, you can never prevent networks, then it will always split sooner or later, too often. Also, if you have more nodes, it will split occasionally, but that's statistics. Like the network I use will split once every 400,000 years. And in the worst case, when they're just a handful of nodes, when they're more, it's more stable. So I can make it more stable, but that just costs more bandwidth, so it just wastes resources. So as I said, you have at least 4 connections then. So I usually use 5 connections because it's exponential. 4 is much stable than, more stable than 3.6, and 5 gives you memory was 100 more times stable or something like that. So I stick to 5 connections too. That's my compromise. More than that is kind of wasteful. So that was the node address announcement. Then you can use random walkers, which I find slightly better. Then you actually, instead of sending these messages, you use one connection and you connect to the nodes and jump around in the network to learn about new nodes, and you keep jumping around. So the first 10 jumps is the same thing as the node address announcement, but then the following 10 goes further and further away, so you will eventually travel around the whole network. Random walkers have some advantages and also some drawbacks, but I prefer them. Now let's see. Here's if you have like 4 to 5 or 6 links, then you have to do 10 jumps between each node you learn about. So if you can't store all of them and try to use them for connections, because if this node suddenly needs 2 new links, those shouldn't be to 2 nodes that were very close to each other when you jump around. There must be at least 10 jumps between them. That's the minimum. Otherwise, you will get misfits. But these numbers depends on how you implement it. So when you decide how to implement it, you have to run the simulation and test when it splits or not. So you have to do it worse and see when it splits, and then you just increase the values a little bit when you're safe. Trying to prove this with math is actually stupid. Many people have done it, but we humans are really I'm not a mathematician, but most of these problems go down to what I think is called combinatorics. And humans, even professional mathematicians, suck at handling combinatorics. So I usually do the math also. So my way of researching is I sit on the sofa for some weeks staring blankly, and I come up with something, then I take paper and pencil and calculator and perhaps my own statistics software, try to do some math and see if it's reasonable. And then I sit for 2 weeks and think how to simulate this, because I don't want to simulate the whole thing. I just want to test the important part, because I can code the whole system, and then I test it. And usually the simulations give other results than the maths. And I have 2 mathematicians that are backing me up in my research, and they usually fail to calculate it. So simulations is the only real approach. And then you can use math to just get the feel of the exact levels, and when those 2 agree, for instance, I usually run my simulations and they will crash. And then I see how often they crash, and then I learn to calculate until my maths say the same number. And then hopefully when I make it stronger, I can calculate that it's probably this strong now. But I'm still not sure, because all my maths always are 2 per mil wrong. It's all of that. No matter what hours, I don't know, it's a curse or something. So usually the simulation is 2 per mil stronger than the math, so I don't know why. I'll give it up.
So 2 per mil?
Sorry? 2 per mil. So for instance, my math said this network will split this often. Right. Simulation split 2 per mil less.
Sorry, what is 2 per mil?
Well, 0.2%.
Right. Yeah.
How do you pronounce that in English properly? 0.2%. You don't use 2 per mil in English. In Swedish we use per mil all the time. Okay, 0.2%. So we don't know why. My mathematician friends, they don't know why. But anyway, there's a third way to do this, which I call it chaos net. This is my own method, but well, I shouldn't waste a day to explain that one.
David, when you simulate stuff, do you have different kinds of simulation software for different problems, or do you